This is going to be one in a series of videos on problem solving and the experimental design part of the higher human course. So this first video I'm going to do will cover double axis graphs and then some calculations from pulling data from graphs as well, or from pulling data from questions. So I've given a list of the questions that I've used for this. So these are the new higher human course assessments, so the final past papers. So the first three questions I'll cover will be from the 2019 paper, questions 15, 17 and 22. And then section B will be the question 9A, B and C, and then the next question I'll cover will be from section B of 2017, which will be question 1E and then 4A part 1, or 4A part 2, and then 4B part 1. Okay, so firstly I'm going to show you this question 15 from 2019. Now, as you'll see, it's a double axis graph. So there's a procedure that you would use when you go and when you approach a double axis graph, which I'll use throughout this whole video. So that procedure basically is that you must highlight each side of the y-axis graph and then which line it corresponds to, but even before you even look at the question that's involved, really, because you need to understand where you're pulling data from. So for example, stroke volume is on the right hand side here in this y-axis. These are the values for stroke volume, and take note of your value, your units, for your stroke volume, so centimeters cubed for stroke volume. Now stroke volume is this cross pointed line, so it would be this one here. So when you're reading stroke volume off, you're reading it off of this green line with the crosses, and you're reading it off of this green side. Okay, so that's the same for this left hand side. So heart rate in beats per minute would use these values here, and as in the unit, like I've just said, is in beats per minute. Okay, it's the dotted line, or the points or dots anyway, and therefore I'm going to colour that in orange, and that will correspond to this left hand side y-axis. Now this question is partly knowledge as well, so you will have to know how to calculate cardiac output, but just for talking sake right now, I'm just going to give you the cardiac output calculation. So cardiac output is heart rate times stroke volume. Now you should know that from unit 2, but so that this is entirely problem solving based, I'm going to give you this calculation. So what you need to do now is figure out what your heart rate is and what your stroke volume is. So for this question, it's asking what is the cardiac output when the rate of oxygen uptake is 0.6 litres per minute. So when that rate of oxygen uptake is 0.6 litres per minute, so this in between 0.4 and 0.8 would be 0.6. So you would then need to use your values from this line here. So you're using this point and this point. So this orange line is heart rate, so therefore you would draw that along. Heart rate is 80 times your stroke volume, which is this point. Now bear in mind this is the green side, so you would have to go along to this side here, and that would be 120. So when you do this calculation and you times these together, you get 9,600 centimetres cubed. And in some questions you'll be asked to calculate that in litres per minute rather than centimetres cubed, so check what your units are for this. For all these, they're centimetres cubed per minute, so you wouldn't have to worry about changing that into litres. So you've got 9,600, and that is your option for C there. Okay, so the next question I'm going to show you is question 17 of the same paper, so 2019, which isn't a double y-axis graph, but it is a multiple graph question. So the graph contains information about the population of the United Kingdom. It gives you in this first graph annual death rate from coronary heart disease per 100,000 people. Okay, so that value is important, is per 100,000 people. The next one is showing population size in millions, and then age in years for males and females. Okay, so we'll look at the question first. So how many males aged between 50 to 59 die of coronary heart disease annually? Okay, so what you need to do is pull this correct data that you need. So 50 to 59 years is here, and the population size is up the side, so we're looking for male for this. So this greyed out line would be males. Okay, so you're going to need to use the information that we've seen there. So from that line here, the population size for males is 3 million. in that age group. Okay, if we move up to this top graph, again it's this greyed out line, or this greyed out bar, sorry. And again note the units here, per 100,000 population. In this bottom graph, the units are millions. So for the males in this scale here, this line which is 400, so 400 males per 100,000 people would be their annual death rate. So if we pull this data down, the deaths are 400 per 100,000, and then the population is 3 million males. So if in 100,000 we have 400 males, we need to find out how much that would then be in 1 million. So there are 10 100,000s in a million. So what you would need to do is do 400 times 10, and that would get you 4,000 in 1 million. Now that population is not in 1 million, it is 3 million. So you would now need to figure out how you would get to 3 million. So hopefully you'll understand how to do this now. So in 3 million, you would then have to take your 4,000 and then times that by 3 to get how many it is in 3 million. And that would give you an answer of 12,000. So then therefore your option would be C again. Okay, the last question I'm going to do from this for a multi-choice will be 22. And this question is a calculation one. Now, people tend to really struggle with these type of questions. So you have to manipulate a number of different units and you have to do a clearly worked out calculation for this. So first of all, what I'll do is I'll highlight the key points for this, which is what you should be doing for all your papers, and then I'll show you a worked example of how to do this. So a drug trial was carried out to study the effect of a drug on mice. A group of mice with an average body mass of 20 grams were given 1 milligram per kilogram of their body mass. The drug was given twice a day for 15 days. What was the total mass of drug given to each mouse over the 15 days? So this is quite a difficult question, and people find this really challenging. So I'm going to show you step by step how to do it now. So, ignoring the options just now, okay, we'll work it out. So the drug is given 1 milligram per kilogram of mass. Okay, and that basically means 1 milligram per 1,000 grams. Okay, because 1 kilogram equals 1,000 grams. Okay, so for every 1,000 grams, they would give 1 milligram. Okay, but we need to find out, we need to basically convert this into grams. Okay, so for every gram of mouse, we need to find out how much drug we would need to give them. So for this then what you would do is you do 1 milligram divided by 1,000, okay, because you're getting 1 milligram per 1,000 grams, and that would give you an answer of 0.001 milligrams. Okay, so for every gram of mouse, we would give it 0.001 milligrams. Now it tells you in this question that the average body mass of each mouse is 20 grams. So for a 20 gram mouse, if they're getting 0.001 milligram per gram, for a 20 gram mouse, you would need to times this by 20. And that would give you 0.02 milligrams of the drug. Okay, so every mouse that's 20 grams worth would get 0.02 milligrams of the drug every time they get a dose. Now the question then tells you that the drug was given twice a day. Okay, so twice a day would mean that that dose that they get, which is 0.02 milligrams, would have to be times by 2. And that would give you 0.04 milligrams a day. Okay, and then it says for 15 days. So for 15 days, you'd have to then times that value by 15. And your answer then would be 0.60 milligrams over the trial. Okay, so therefore for this then your answer would be D. Okay, so I'm just going to move that up slightly, just so you can take a screenshot if you need to. Okay, the next question then will be the main section of the paper, which is question 9. And we're going back to a double y-axis graph this time. So again, the first thing you need to do is then highlight the y-axis sides. So this one is blood glucose concentration. And then blood glucose is this this crossed off line here. Okay, we'll do the same on the other side. So this dotted line corresponds to this y-axis here, which is blood insulin concentration in units per litre. So again, pay attention to your units here. Okay, so the question talks about how glucose tolerance test if you had type 2 diabetes. So it basically just describes what you're shown in this graph. So initially what the question is asking you to do is state the man's blood insulin concentration when his blood glucose concentration was 200 milligrams per 100 centimeters cubed. So they're giving you his blood glucose concentration. So if you look at the blood glucose concentration at 200 milligrams, this is blood glucose, that's your 200 milligrams per 100 centimeters cubed here. It's asking for what his blood insulin concentration is at that same point. So on that same time of 30 minutes, this is the person's blood insulin concentration. So you need to read it off of this orange side here. So if you follow over, that'd be 300. And again, it's units per litre, which they have given you as their units here. So 300 would be your answer. Now the next question asks, the man's blood glucose concentration, I'll move this up. The man's blood glucose concentration will eventually return to its original value. Predict how much longer it will take after this 150 minutes. So the original value, first of all, you'll need. Okay, so man's blood glucose concentration will return to its original value. So blood glucose original value. So if we look at blood glucose, the original starting value here was 145 milligrams per 100 centimeters cubed. Okay, this was his original value. Now it's asking you to predict how much longer it will take after this period of 150 minutes to reach that 145. So for this question, we're looking at the green line here, okay, which is the blood glucose concentration. Now if you look at how much it has dropped by and what the pattern is, okay, it's dropped by 3 boxes, okay, over that period of 30 minutes. Okay, and 3 boxes essentially is 15 milligrams per 100 centimeters cubed. Okay, because each box is worth 5 milligrams. Okay, so each box is worth 5 milligrams per 100 centimeters cubed. So if it's dropping by 3 boxes over that 30 minutes, that means it's dropping by 15 milligrams per 100 centimeters cubed. Okay, so for this, every 30 minutes, it drops by 1.5 milligrams. Okay, and at 150 minutes, the value is 205. Okay, so I've pulled some data there that you'll need to use to then figure out this prediction. So your end value, what it finished with at 150 minutes, is 205 milligrams. You're looking to find out how much longer it'll take to get to 145 milligrams, including the fact that it drops by 15 milligrams every 30 minutes. So if at 150 it was 205, at 180 in the next 30 minutes, it would then be 190. Okay, it drops another 30 minutes to 100, it goes another 30 minutes, so it increases by another 30 minutes. So that's 210 minutes. Okay, and that would then make it drop to 175. So all these values here are milligrams, all these values here are time. So then it goes to 240 minutes, and that would drop to 160 milligrams, and then another 30-minute jump would be 270 minutes, and then that drops to 145. So that is us returned to our original value. So in terms of how much extra time, it's not just that it leads to 270, it's asked for how much longer will this take after the 150 minutes. So the difference between 150 and 270 minutes is 120 minutes. That's how much longer it takes. Again, this is a really complex question. It takes a lot of working out. Okay, now the next question relates to a calculation from this graph. So I'm going to show you the question, then I'll go back to the graph. So this man's body contains 5 litres of blood. Calculate the total mass of glucose in his bloodstream at 60 minutes. Okay, so we're looking at glucose in his bloodstream at 60 minutes first of all. Okay, so blood glucose at 60 minutes. So this is at 250 and it's milligrams per 100 centimetres cubed. Okay, and that's at 60 minutes. Now this is in 100 centimetres cubed. So now you need to do is calculate that up to 5 litres. So in 100 centimetres cubed we have 250. So in a litre, which is 1,000 centimetres cubed, we have 250 and would need to times that by 10. And that gives us 2,500. So that's getting into 1 litre. To get it into 5 litres, you have to multiply this by 5. So your answer then would be 12,500 milligrams. Okay, I'm going to move on to the 2017 paper now. So we'll start with question 1E, which is a double y-axis graph. Again, this information will be important to some questions. For these ones, fortunately enough, it's not, so I'll not really involve myself with this blurb for this question. So again, you do the same as we've done before. Highlight the sides, so highlight the y-axis. So white blood cell count is here. This is your values for it here. And then white blood cell count is this straight line with no dots in it, no breaks. Your other side, which is the dashed line, will be the chance of infection. So the question asks, the very first question, asks, state the chance of infection after treatment when the white blood cell count was 0.7 times 10 to the power of 9 per litre. So white blood cell count was 0.7. So that's halfway in between 0.6 and 0.8. So when that white blood cell count was 0.7, it's asking for the chance of infection. So on that same day, that chance of infection is here. So you pull that line along, and that would then be 15%. Okay, the next one, part 2, is saying predict the white blood cell count 7 days following the chemotherapy treatment. So for this one, all you need to do is actually just project your line and calculate or continue on in the same angle it was before. Okay. Now, the first thing that people tend to do is they then go, oh, well, that's 2.5, and that's what the value is. But that's not the case. You have to use the pink side like we've followed on, okay? So just to highlight that here, this is your pink line. So your pink side would be 0.1. And they've given you your units already. The next question I'm going to cover is question 4. This will be the last one, you'll be glad to know. This is another double y-axis graph. Now, I'm not going to do the first part of this question, which is describing the role of estrogen, because that's part Unit 2 knowledge. So all I'm going to do is the same as what we've done before, which is highlight these y-axis sides. Okay, so plasma concentration is on this side, and it's plasma concentration of estrogen. So it's this dotted line. Okay, or sorry, the dot points. Okay, the next side then will be this dashed line, which is the thickness of the endometrium. Here's your values, and there's your label with your units. Okay, so the question asks, state the thickness of the endometrium on day 15. So all you need to do is go to day 15. And find the thickness of the endometrium. The thickness of the endometrium is this yellow line. So we're looking at this value here. Okay, now this is 3 here, so that one box above it is 3.1 millimeters. Okay, so I'll just show you that here. So this value here, following it along, 3.1. Okay, and the last question is asking you to express as a simple whole number ratio, so that means without any decimal points in it, the thickness of the endometrium on day 6 compared to day 22. Okay, so I need to get the values first. So thickness of endometrium is the yellow line. Day 6 is here. So day 6 is 1.2. And day 22 here is 4.8. Okay, so I'm going to move that across. So day 6 is 1.2, and day 22 is 4.8. And make sure that these go in the right order, so you must follow the order that they've given you here. Day 6 and day 22 are in the correct order. So to do a simple whole number ratio, the best way to do it is to actually divide the smallest one by itself. Normally this works, okay? Either that or find a common denominator that divides into both. So 1.2 divided by 1.2 would give you 1. And 1.2 divided into 4.8 would give you 4. So your value then for your simple whole number ratio is 1 to 4. Okay, so that runs through double y-axis graphs, pulling data from them and also doing some calculations from questions.